In this example, a student hangs a spring from the ceiling. She then hangs a 34.5 kilogram mass on the end of the spring, and the spring stretches negative 59.1 centimeters. The negative simply means the spring is stretching downwards. She then uses her hand and pulls the mass downwards, stretching the spring an additional negative 35.0 centimeters. When she releases, the mass starts bobbing up and down. And the question is, what's the period of the mass's motion? Now, equation 10.11 allows us to calculate the period of a mass in motion like this, but that equation requires the spring constant, K, and we don't have that yet. So our first job is to calculate the spring constant. Well, that's not too hard. We've already done it in example 10.1. When the mass is added to the spring, its weight pulls the spring down, and the spring will continue to stretch until the restoring force is equal to that weight. So let's calculate the weight. Weight equals mass times g. The mass is 34.5 kilograms. G is 9.8 meters per second squared. So the weight is 3.4 times 10 to the 2 newtons. The spring will stop when the restoring force equals that weight. The restoring force is given by force equals negative k delta x. The spring will stop stretching when the restoring force equals the weight. So the force is 3.4 times 10 to the 2 newtons. We don't know k, but delta x is negative 59.1 centimeters. We need to convert that into meters to make the units work out. So that's negative 0.591 meters. I've got two delta x's here. Why did I choose the first one? Think about it. The first delta x comes when the weight is initially attached to the spring. The spring stretches and everything stops when a new equilibrium point is achieved. That's the delta x that will allow us to calculate k. What's the other delta x in the problem? Well, that's the distance that the student stretched the spring in order to start the mass bouncing up and down. That certainly starts the simple harmonic motion, but it doesn't tell us about k. We can calculate k by finding the distance that the spring stretches in order to get to a new equilibrium position. That's the first delta x. Okay, now we can find the spring constant. We divide both sides by 0.591 meters, and the spring constant is 5.8 times 10 to the 2 newtons per meter. Now we can use equation 10.1, which says that the period is 2 times pi times the square root of the mass, 34.5 kilograms, over the spring constant, which we just calculated, 5.8 times 10 to the 2 newtons per meter. When we work all of that out, we find that the period is 1.5 seconds. This means it takes 1.5 seconds for the mass to travel from the place which it was released up and then to return to the place at which it was released. That entire trip up and back down takes 1.5 seconds. Now, before we end this problem, I want you to notice we never used that additional stretch. That negative 35.0 centimeters never came into play. Why? Well, that additional stretch just tells us how far the mass has to travel as it oscillates back and forth. However, the period of the mass's motion does not depend on that. The period of the mass's motion depends only on the mass and the spring constant. So that additional stretch is simply extra information you never use.